Hello everyone. Today I'll be presenting my research paper on deep learning enhanced single station Wi-Fi localization for social networking in smart environments, a collaborative work uh, with my colleague Professor Muhammad Al-Hubayshi from Halij University, Istanbul, Turkey. This presentation will dive into how we can leverage deep learning techniques to achieve accurate indoor localization using just a single Wi-Fi access point, a method that promises to simplify deployment and reduce cost in various smart environments application where location-based services are increasingly vital. Many of you are aware, accurate indoor positioning is a cornerstone for multitude of location-based services. These services are transforming sectors such as healthcare for patient and asset tracking, retail for personalized customer experience, and industry for optimizing logistics and automation. However, the global positioning systems or GPS which we rely on outdoors is largely ineffective inside buildings due to the single attribution and interference caused by building materials. This brings us to the challenge of indoor localization. While various technologies have been explored, Wi-Fi based systems have gained prominence due to the usability of Wi-Fi infrastructure. Traditional Wi-Fi localization often employs multiple access points, or APs, to triangulate or fingerprint device positions. While effective, these multi-AP systems can be complex and costly to deploy and maintain, especially in dynamic environments. This is where the motivation for our research comes in. The need for a more cost-effective yet still accurate single access point solution. Our research explores the potential of a single access point Wi-Fi localization. While this approach significantly reduces hardware requirements and deployment complexity, it also presents unique challenge primarily related to single noise to the inherent variability of Wi-Fi signals, and the limited features available from a single reference point. To address these, we propose a solution that utilizes standardized feature scaling and a robust neural network architectures. Furthermore, we incorporate class balancing techniques such as SMOTE and focal loss to handle the common issue of imbalanced datasets in the real-world scenarios. Our primary objective is to demonstrate that single access point systems, when enhanced with these advanced data processing and deep learning methods, can achieve high accuracy and offer a practical and feasible alternative for indoor localization in smart environment. To better understand our approach, let's briefly review some background concepts. Single access point localization, as the name suggests, aims to determine a device's position using signals from just one Wi-Fi access point. This inherently reduces hardware requirements and simplifies deployment compared to multi-access point systems. However, it places a greater burden on sophisticated signal processing and modeling techniques as we have only one reference point to overcome the common challenges of Wi-Fi signal propagation. One of the primary challenges is the nature of received signal strength, or RSS data. Wi-Fi signals are susceptible to environmental factors such as reflections of walls, furniture, and even people, leading to complex fading profiles and multipath interference. These factors can cause significant variation in RSS readings, even at the fixed location. In a single access point scenario where we lack the cross-validation capabilities of multiple anchors, robust filtering, outliers management, management, and data adaptation can become absolutely essential. Failing to adequately address the environmental interference can severely degrade localization accuracy. This is where deep learning offers significant promise. Neural networks, with their ability to learn complex nonlinear patterns from large datasets, are well suited to tackling the challenge of noisy and variable RSS data. Our architect like convolutional neural networks can process signal intensity maps, while recurrent neural networks such as LSTMs can capture temporal dynamic, which is useful for tracking moving devices. As highlighted in the literature and detailed in section 2 of our paper, effective data creation, including standardization and feature engineering, is crucial. Even the most advanced neural network can be hampered by poorly prepared input data, especially given the inherited noise uh, in a single vantage point. Furthermore, a common issue in real-world localization datasets is class imbalance. Some areas are visited more frequently than others, leading to overrepresentation of these locations in the training data. Deep learning approaches are combined with techniques like SMOTE for oversampling a minority classes or special or specialized loss function like focal loss are increasingly critical for ensuring model uh, that the model will perform well across all areas, not just most popular ones. Now let's talk about the methodology that we used in our paper. Our system architecture, as shown in slide number 4 and figure number 1 in our paper, outlines a comprehensive pipeline. This pipeline begins with data collection from a single Wi-Fi access point, proceeds through rigorous pre-processing and model training, and culminates in deployment and evaluation. The key parameters that were collected: received signal strength, RSS measurement, the known distance of the device from the access point, and critically the precise location label, which served as the ground truth for training our localization models. Following data collection, we undertook extensive data pre-processing. This is a vital stage, particularly for single access point systems. Our pre-processing involves several key steps. First, cleaning the noisy RSS data to remove outliers and inconsistencies. Second, applying standardized scaling to ensure that features with larger numerical ranges do not disappropriately influence the model. Third, inputting any missing values to maintain dataset integrity, and importantly, addressing class imbalance as mentioned earlier. Some locations are naturally more represented in the dataset. We employ techniques such as SMOTE to generate synthetic samples for underrepresented classes, alongside strategies like class weighting and the use of focal loss function during model training to give more importance to minority classes. The pre-processed data we moved to model training. We evaluated 4 distinct neural architectures. Our focus was to identify an architect that could effectively learn the complex pattern from the single access point Wi-Fi signals while being robust to noise and class imbalance. As well, we will discuss the results a deep neural network, specifically optimized with a combination of SMOTE and the focal loss function, demonstrated superior performance. Finally, for deployment consideration, all our experiments were conducted on a standard hardware setup. We carefully evaluated not just the accuracy, but also the inference latency to ensure the real-time applicability of our proposed system in practical smart environment applications. Now talk about the results of our experimental evaluation. Our findings are quite encouraging. The deep neural network model, when combined with SMOTE for oversampling and the focal loss function, achieved a remarkable performance. Specifically, we observed macro F1 scores exceeding the 0.97 and overall accuracy suppressing 95%. In our controlled test environments, this is a significant result as it demonstrates the model effectiveness in handling the challenges of data imbalance and inherent signal noise, which are critical hurdles for signal access point localization systems. The high macro F1 score is particularly noteworthy because it indicates that the model performs well across all location classes, including those that were initially underrepresented in the dataset. This balanced performance is crucial for the reliability of any practical indoor localization. Beyond accuracy, computational efficiency is a key factor for real-world deployment. We found that our optimized DNN model maintained excellent efficiency. The inference times, that is the time taken to predict a location from a new Wi-Fi data, remained below 5 milliseconds on standard hardware. This low latency confirms that the stability of our approach for real-time localization tasks in dynamic smart environments where quick response are often necessary. So what are the practical implication of these findings? Our research strongly suggests that single access point Wi-Fi localization, when enhanced with robust data creation and specialized deep learning techniques, offers a genuinely economical and flexible solution for indoor positioning. The ability to achieve high accuracy with reduced hardware complexity opens up possibilities for a wider adoption in various settings, particularly for those that are cost sensitive or require frequent recognition. Furthermore, our paper discusses strategies for adapting these models to dynamic environmental changes, which is an important consideration for the long term deployment. In conclusion, our research underscores the viability of single access point Wi-Fi localization as a practical and effective solution for smart environments. We have demonstrated that through robust data creation, including multi-use pre-processing and balancing combined with specialized deep learning models, it is possible to significantly improve positioning accuracy even with the inherent limitation of a single access point. The key methodological advancement from our work include the successful integration of smooth oversampling with focal loss function with a deep neural network. This combination has proven particularly effective in addressing the previous challenges of class imbalance and environmental noise that often affect Wi-Fi signal data. The system we developed not only achieves high accuracy but also demonstrates effectiveness, computation, and a degree of adaptability, which are crucial for real-world deployment in cost-sensitive and dynamic indoor settings. Looking ahead, there are several exciting directions for future work. The model can be tested more extensively in diverse real-world environments. Evaluating performance under varying conditions and in more dynamic placement will be key to ensure its robustness and generalizability. Secondly, uh, it can explore sensor fusion, potentially integrating data from other sensing modalities such as interior measurement units from smartphones or Bluetooth signals to further enhance positioning accuracy and reliability. Further research will also focus on improving the adaptability of the system, developing techniques for faster model retraining, or even online capabilities could significantly reduce downtime and maintenance efforts when environmental change occur. Uh, Finally, deployment, pilot deployments in practical settings like smart homes, retail space, and healthcare facilities. These real-world pilots will be invaluable for testing practical feasibilities of our system and gathering user feedback to refine it even further. That brings me to the end of my presentation. Thank you all for your time. If you have any questions regarding my research paper, please contact us via the email as shown on the slide. And thank you once again.